So in this video, we're going to study rational functions. Let's begin by defining a rational function. A rational function is a function f that is a quotient of two polynomials. That is, f of x equals p of x over q of x, where p of x and q of x are polynomials, and where q of x is not the zero polynomial. The domain of f consists of all inputs x for which q of x is not equal to 0. So a rational function has to be a fraction, a rational expression, and the numerator and the denominator of the rational function have to be polynomials. So let's take a look at some examples of rational functions. So here I have some rational functions and their graphs. So this is the most basic rational function, f of x equals 1 over x. So again, we have a polynomial over a polynomial. In the numerator, we have just the constant polynomial, p of x equals 1. And in the denominator, we have the polynomial q of x equals x. That's the identity polynomial. And this is what the graph of that function looks like. Here we have another polynomial function, f of x equals 1 over x squared. And here's what the graph of that polynomial function looks like. Here we have a more complicated polynomial function, f of x equals x minus 3 over x squared plus x minus 2, and this is what the graph of that polynomial function looks like. And then we have a few more examples of polynomial functions. F of x equals 2x plus 5 over 2x minus 6. Here's what that looks like. F of x equals x squared plus 2x minus 3 over x squared minus x minus 2. Here's what the graph looks like. And finally, f of x equals negative x squared over x plus 1. Now I want to point out some characteristics of these rational functions. This is what rational functions typically look like. So notice there are some characteristics. First of all, these functions have breaks in them. These are called discontinuities. And more specifically, if we take a look, for example, at this particular function, f of x equals 1 over x, this break that occurs in the graph, this graph keeps going down over here to the left of the y-axis, and then it goes up forever to the right of the y-axis. So the y-axis in this particular function is called a vertical asymptote, and we're going to talk more about vertical asymptotes a little bit later on. Also notice that as x gets bigger and bigger and bigger, this graph keeps getting closer and closer to the x-axis, and the same thing happens over here on the left-hand side. As x gets to be a bigger and bigger negative number, the y value gets closer and closer to the x-axis. That's called a horizontal asymptote. And so this graph keeps getting closer and closer to that, and we're going to be talking more about horizontal asymptotes as we move along as well. So a key characteristic of rational functions is that we often have these kinds of asymptotes. So we can see here for this graph, for example, the y-axis is a vertical asymptote. This graph's going to keep getting closer and closer to it as we get closer and closer to 0. And we also have this horizontal asymptote here. If we take a look at this particular graph, there is a vertical asymptote, it looks like around here, and there is a vertical asymptote, it looks like around here. So again, over here, this graph's going to keep getting closer and closer to that vertical line. Over here, it's going to keep getting closer and closer to that line. This vertical asymptote, the graph's going to keep getting closer and closer to that line. Same thing over here. This graph's going to keep getting closer and closer to that vertical line. And in the same way, we have this horizontal asymptote here. So again, I think I've discussed that enough, but this is a key characteristic for most rational functions, is that we're going to have these types of asymptotes. Notice on this one, we have a vertical asymptote. It looks like around here, but this one doesn't really have a horizontal asymptote. This one has what's called an oblique asymptote, So there is this slanted line that this graph keeps getting closer and closer to, and we'll discuss those a little bit later on as well. So this is what rational functions are going to look like as a general rule. They have these kinds of characteristics. Now if I pull back in our definition for a rational function, I want to re-examine this last sentence. The domain of f consists of all inputs x for which q of x is not equal to 0. So we cannot have the denominator equaling 0. If the denominator equals 0, that causes division by 0, which of course is not allowed. And we've studied this previously, but I want to revisit that now that we're looking specifically at rational functions. So take a look at this example. Consider the rational function f of x equals 1 over x minus 2. Find the domain and graph f. So the domain is going to consist of all real numbers except anything that causes division by 0. So what we need to do is take a look at the polynomial function in the denominator, in this case x minus 2, set that equal to 0 to determine what's going to cause the denominator to equal 0. And the domain of our rational function will be everything except whatever causes that division by 0. So if we take x minus 2, set that equal to 0, and solve, well, if we add 2 to both sides, we get x equals 2. So that means 2 would cause division by 0 in this function. And you can see that, right? If I ask you to find f of 2 would equal 1 over 2 minus 2, which would be 1 over 0, which is undefined. So we can't find f of 2. So the domain of this function is all real numbers except 2. So x can be anything except 2. So if you'll recall, we can write that this way in set builder notation, or if we wanted to use interval notation, x can be anything from negative infinity to 2, or it can be anything from 2 to infinity. So we can write it this way in set builder notation, or we can write it this way in interval notation. And again, we've done that previously, so this should be primarily a review. Now, the next thing that we need to do, we found the domain, we want to graph this function. Well, one way that we can graph this function is just by substituting values into this function for x. So in other words, we can make a table of values. So let's do that. So for example, we know we can't let x equal 2, but I could let x equal 1. And if x equals 1, then f of 1 would be 1 over 1 minus 2. 1 minus 2 is negative 1, so that's 1 over negative 1, which is negative 1. So we would have the point 1, negative 1 on this graph. So if I draw my x-axis and my y-axis, and let's say here's 1, 2, 3, 4, 5. Here's negative 1, negative 2, negative 3, negative 4, negative 5. 1, 2, 3, 4, 5. And negative 1, negative 2, negative 3, negative 4, negative 5. Let me label here. So we have found that the point 1, negative 1, 1, negative 1 is a point on this graph. So what if I let x be, say, 0? Well, if x is 0, then f of 0 is going to be 1 over 0 minus 2, which is 1 over negative 2, which is negative 1/2. So 0, negative 1/2. So 0, negative 1/2 would be here. What if I let x be negative 1? Then if I find f of negative 1, then I would get 1 over negative 1 minus 2. Negative 1 minus 2 is negative 3, so I have 1 over negative 3, which is negative 1/3. So I have the point negative 1, negative 1/3, which is here. And so on. I could continue to substitute values for x. Now, remember that x can't be 2. So what happens if I were to let x be something maybe close to 2? Like, let's say, what if I wanted x to be 1.5? So if I let x be 1.5, which I'm going to write as 3 halves. Well, if I find f of 3 halves, then that would be 1 over 3 halves minus 2. Now, to find 3 halves minus 2, I would have to find a common denominator, so that would be 1 over 3 halves minus 2, written with a denominator of 2, would be 4 halves. So I would have 1 over 3 halves minus 4 halves, which would be 1 over negative 1 half, and 1 divided by negative 1 half would be negative 2. So at 3 halves, which would be here, I get negative 2. What if I were to let x be something even closer to 2? For example, what if I let x be, say, 1.9? Well, if I find f of 1.9, then I'm going to have 1 over 1.9 minus 2, which would be 1 over negative 0.1. And 1 divided by negative 0.1 would be negative 10. So as I get close to 2, here would be negative 6, negative 7, negative 8, negative 9, negative 10. As I get close to 2, this value becomes a bigger negative value. So what's actually happening, I mentioned earlier that we had these vertical asymptotes. So this vertical line that I just drew in as a dotted line is the vertical line x equals 2. This graph is going to get closer and closer and closer to that vertical line, but it can never actually touch that line. And as I go this way, this graph is going to keep getting closer and closer and closer to the x-axis, but it can never actually touch the x-axis. Now, I didn't write in my value here, negative 10. What if I substitute in values bigger than 2? Like what if I substitute in the value 3? Well, if I substitute in the value 3, let's do this over here. F of 3 would be 1 over 3 minus 2, which would be 1 over 1, which would be 1. So I get the 0.31, which would be here. What if I substitute in the value 4? Well, f of 4 would be 1 over 4 minus 2. And 4 minus 2 is 2, so that's 1 half. So I have the 0.4 1 half. If I were to substitute in 5, I would get even closer to the x-axis. 6, I would get even closer to the x-axis. So this graph is getting closer and closer to the x-axis the bigger I let the value of x be. What if I let the value of x get closer and closer to 2? Like what if I let x be 2.5? So if I let x be 2.5, I'm just going to use a decimal point this time. Then f of 2.5 would be 1 over 2.5 minus 2, which would be 1 over 0.5. And 1 divided by 0.5 would be 2. So at 2.5, which would be here, the y-coordinate would be 2. So this graph is doing the same kind of thing over here. It's turning and it's getting closer and closer and closer to that vertical asymptote. Like for example, if I were to let x be, say, 2.1, then f of 2.1 would be 1 over 2.1 minus 2, which would be 1 over 0.1, and 1 divided by 0.1 would be 10. So if I'm just barely to the right of 2, I go up really high. I go up to 10. So this graph looks like this. We have a vertical asymptote here at x equals 2, and we have a horizontal asymptote here at the x-axis, which the equation of the x-axis is the horizontal line y equals 0. Now again, we're going to be studying these a whole lot more as we move forward. I want to look at one more example and then we'll switch to a different video. Before we start the next example though, let's take a look at this graph on the graphing calculator. If I go to y equals, I'm going to enter this as 1 divided by the quantity x minus 2. We have to put that x minus 2 inside parentheses. And if I do a zoom 6 for our standard graph, here is what that graph looks like. So again, we can kind of see that we have the vertical asymptote going on here at x equals 2, and we have this horizontal asymptote occurring here at the x-axis, which is the equation y equals 2. Now, let's go ahead and pick up our next example. So in this example, we have 5 parts, and we want to find the domain of each of these rational functions. So in part A, we have the function f of x equals 1 over x. So again, we can't divide by 0. So in this case, this x cannot equal 0. So our domain for this function is going to be that x can be anything as long as it's not 0. So this is set builder notation, or if we write that in interval notation, x could be anything from negative infinity to 0, or it could be anything from 0 to infinity. It just can't be 0. And so we call this again the union symbol. So negative infinity to 0, union 0 to infinity. Taking a look at part B, we have the same issue. In this case, it's x squared that can't equal 0. But if x squared can't equal 0, that means that x can't equal 0. So our domain for part B is the same as for part A. X can be anything except 0, or if we write that in interval notation, anything from negative infinity to 0, union anything from 0 to infinity. Taking a look at part C, we have the function f of x equals 2x over x minus 1. So to find the domain, we're going to take the denominator, set it equal to 0, so set x minus 1 equal to 0, add 1 to both sides, so x equals 1. So if x equals 1, the denominator is going to equal 0. So our domain means that x cannot equal 1. So our domain, x can be anything as long as it's not 1. Or, that could be anything from negative infinity to 1, union 1 to infinity. So again, x can be anything except 1 because 1 causes division by 0. Taking a look at part D, we have a little bit more challenging problem here. We have x squared minus x minus 2 that we need to set equal to 0. So that is a quadratic equation that we can solve. Remember, we can solve quadratic equations by factoring if they'll factor, by using the square root principle, or by using the quadratic formula or completing the square. In this case, this will factor into x minus 2 times x plus 1. So by the zero product principle, that means that either x minus 2 equals 0 or x plus 1 equals 0. So x equals 2 or x equals negative 1. So if I ask you to find f of negative 1, that's going to cause division by 0, which can't be done. If I ask you to find f of 2, that's going to cause division by 0, which can't be done. So the domain is that x can be anything except those two numbers. So for part D, for our function f of x equals 1 over x squared minus x minus 2, the domain is that x can be anything as long as it's not negative 1 and as long as it's not 2. And I just put those in order. Negative 1's farther to the left, 2's farther to the right, so I put those in order. So x can be anything except negative 1 or 2. Or if we want to write that in interval notation, x can be anything from negative infinity to negative 1, union. It can be anything from negative 1 to 2, union. It can be anything from 2 to infinity. So again, anything from negative infinity to negative 1, union. Anything from negative 1 to 2, union. Anything from 2 to infinity. And our last problem We have f of x equals x plus 1 over x squared minus 4x minus 5. So this is similar to part D. We need to see what would cause division by 0. So we're going to take the x squared minus 4x minus 5, set that equal to 0. Again, that's quadratic, so we can solve it by factoring if it factors, quadratic formula, square root principle, completing the square, any of those will work. In this case, it will factor into x plus 1 times x minus 5. So either x plus 1 equals 0 or x minus 5 equals 0, which means x equals negative 1 or x equals 5. So our domain is that x can be anything as long as it's not negative 1 and as long as it's not 5. It can be anything else. If I write that in interval notation, negative infinity to negative 1, union, negative 1 to 5, union, 5 to infinity. So again, x can be anything from negative infinity to negative 1, or it can be anything in between negative 1 and 5, or it can be anything from 5 to infinity. So here we have found the domain of each of these rational functions.